Hello, can you hear me?
Hello. So shall we start?
Yeah, I'm ready whenever. I can share my screen. Yeah, whenever you want, I can share my screen and can get started.
Good afternoon, dear participants. It is with the great pleasure that I introduce to you Professor Rajiv Gupta, North Carolina State University, USA, a distinguished expert in material science and engineering. With a remarkable background and extensive experience in his field, Professor Gupta brings a wealth of knowledge and expertise that transcends institutional boundaries. He has earned his BTech in Materials and Metallurgical Engineering from the prestigious Indian Institute of Technology, Kanpur, followed by his PhD in Materials Engineering from Monash University, Australia. Professor Gupta has consistently demonstrated a deep commitment to academic excellence throughout his career. Prior to his current position, Professor Gupta served as an assistant professor of chemical, biomolecular, and corrosion engineering at the University of Akron, Ohio, where he made significant contributions to the advancement of research in his field. His dedication and passion for his work have been recognized through numerous accumulates, including the NSF Career Award, ECS Rusty Award, AMPP Educator Award, and ACA Brain Cherry Award. With over 130 publications and two patents to his name, Professor Gupta's contribution to the field are both prolific and impactful. As an associate editor of the Journal of the Electrochemical Society, he continues to shape the discourse within his discipline, further solidifying his reputation as a thought leader in material science and engineering. Today, we are honored to have Professor Rajiv Gupta with us. We eagerly anticipate gaining insights from his expertise as we collectively strive towards excellence in our faculty development program. Please join me in extending a warm welcome to Professor Gupta. Over to you, sir.
Thank you so much for nice introduction. Uh, I really appreciate that. I wanted to thank you for inviting me today, and I'm looking forward to this talk. And then I will stay here, I think, to talk to you for an hour or so after the talk. So, uh, uh, so what I'll do is I'll share my screen and get started. Uh, let me see how to share that. All right. Can you see my slide? And can you hear me? Please let me know if I'm audible and if you can see my slide. You can write in the chat. I opened the chat box. All right, great. All right, so I'll get started. So what I'll do today is I'll talk about lightweight, high strength, and corrosion resistant and recyclable metallic materials. I understand the theme of this workshop or conference is recent trends, challenge, and future roadmap. So what I'll do is I'll try not to go too deep in the corrosion, which is my main research field. I'll try to give a general overview of kind of the future of metallic materials and how kind of corrosion could help in kind of in transitioning technologies in future, how it could kind of help in making the material available which are needed for the future technologies, right? All right. So, oh, my voice is very low. Uh, all right. Is this better now? Anyway,
Sir, you are not audible.
yeah. Is this better now? I
Ah,
was
yes,
trying to see.
yes. Yes,
Okay.
sir, now.
All right. Okay. Let me know if I'm not audible or something. So, I'll yeah.
Yes, sir.
All right, I'll just keep going. So, what I'll do today is basically I'll just give a brief overview of the metallic materials and corrosion. Then I'll give two examples, kind of just to show what the future lies, right? So, looking at the corrosion, we all know what corrosion is, right? Corrosion is basically defined as the degradation of the materials we use in the daily life. It could be the metals, could be polymers, could be ceramics, and so on, right? And corrosion or the material degradation is general term you use. There's really good book here, Rust the Longest War, which defines the corrosion pretty well. So when people
Yes.
started using kind of the metal for very first
Excuse
time,
me, sir. Screen is not visible.
oh, screen is not visible.
Ah, yeah.
Stop share.
Full screen mode.
Yeah, is this better now? Can you see that now?
No.
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 Uh, Can you see it now?
No, sir. Double click to enter full screen mode.
Yeah, I did that.
Um,
Okay, let me see. I'll try another way. I'm sharing my PowerPoint. Let me share the screen. Can you see it now? I'm sharing my desktop. Can you see it now?
no, sir.
No. Okay. Uh, I don't know what's problems.
So initially it was seen.
Yeah. Let me see it again. How about now? Or do you want me to do
No.
one thing the
Huh.
old way, like maybe I'll just sign out and sign in again? That
Okay.
might work.
Now, yes.
Okay, so what I'll do is I'll sign out and then sign in again.
So now it is visible. Yeah. So you are mute.
All right. Oh,
Ah,
okay.
yes.
All right. So I'll keep going. The slides are visible now, so I'll
Yes,
keep.
sir. Yes.
All right. So I'll just start where we were. So we were talking about kind of just giving a background what corrosion is, and we all know that corrosion is basically degradation of the metals or the material we use. And corrosion has been like problem since people started using the metal. The way you can think is like we extract the metals from the ores, and ore is more thermodynamically stable state. So what metals try to do is they try to go back to this more thermodynamical stable state, which is kind of oxides, chlorides, sulfates, and things like that. So once we put the metal in any environment, they tend to corrode, right? And this been happening since we started using it. And the corrosion been like problem when we started using that in our daily life or in industrial, applications. The corrosion been problem in kind of all the industrial sectors. So in the left hand side, you'll see some of those examples. So long back in 1949, a professor in MIT, Professor Ulick, he tried to estimate the cost of corrosion. It was like 2.5% of the GDP at that time. And in 2016 and 2013, NAS tried to estimate the cost of the corrosion. It was 3.5% of the GDP, which is like $2.5 trillion annually, which is huge cost of the corrosion. One fact is really important here. If you notice this cost of the corrosion and you look at the studies being done from say 1950s until now, cost of the corrosion kind of varies from 3 to 5% of the GDP. And this doesn't include a lot of indirect impact of the corrosion. If you include that, the cost would be probably a lot higher. So anyway, uh, uh, is uh, is my voice is okay now or still that low?
Yes, sir. Your voice is okay.
Oh, all right. I was just seeing the message probably for a long time. All right. So this corrosion has been kind of that big problem, and we really need to do something about that, right? And that's where a lot of my research is focused, and a lot of people working on that. So the cost being one factor. Now looking at the sustainable future and looking at the environmental materials you need, how can we kind of fight with the issue of the environmental issues and the global warming and all those kind of the issues. So, I mean, a lot of people kind of working on new clean energy generating system and things like that. From the material perspective, what we really need to help there is we really need the material which can give really high fuel efficiency. And the way we can do is we can make the material lighter, right? So like say for example, use of say magnesium or lighter materials like aluminum and things like that. But there's own challenges and corrosion comes there, right? So for example, one of the big factor which is not allowing use of magnesium is the corrosion. They're very active metal and corrode really fast. Recycling and reuse, that's kind of really important. Like whatever we use, we need to be able to recycle and reuse those things. And we think that metals are really recyclable, but in reality, like if you look at the aluminum, a lot of the metals really not recyclable. Looking at, for example, aluminum flying those all those aircrafts, there's so much aluminum flying in the air all the time, right? And once it's come to recycling, it's really hard. I mean, recycling aluminum to again a high performing aluminum alloys is really challenging. And again, the corrosion comes into the picture over there. You have some iron impurities, and they cause huge corrosion issues. And we'll talk a little bit about that today. Decreasing the material consumption, right? So one way to look into that is we can increase the strength of the material and kind of the can decrease the required amount of the material needed, right? And decreasing the need to produce, right? And these kind of two factors, material consumption and need to produce, comes like hand by hand. So increasing the service life of those components, probably we can use these components for longer time, recycling them. So our need to to produce them every time would decrease. Recycling becomes very important. Uh, Making the material, making the say extracting the metals from ore is really energy extensive process, right? I mean, if you can just reuse the material, just recycle them, that could save a lot of energy, right? And we need really new materials which can withstand the harsh environment. So, for example, we try to increase the efficiency of our fuel generating system, efficiency of the vehicles, efficiency of our turbines. Every time we need to increase the temperature a little bit, and we really struggle in finding the right material over there, right? So we really need the material which can really withstand those corrosive environment. And I think what really we need is in terms of kind of having this material for the future, which will be energy efficient or which would provide the materials needed for future energy generation. This should be lightweight, high strength, huge compositional tolerance. Like it shouldn't, like a lot of time we look at the material, but there is a very fixed composition, and a little bit change in the composition would cause huge difference in the properties. And having such material becomes very difficult to kind of recycle them. So having huge compositional tolerance helps in recycling and decreasing the need of a lot of material, should be damage tolerant, corrosion resistance, should be manufacturable, and again we don't want to pay a lot of money for that. So we really need the material which are kind of well beyond whatever the commercial alloys we have today, right? So looking at the kind of options we have, just the pure elements, and kind of looking at the density or the weight point of view, uh, if you look at aluminum here, you see 2.7 gram per centimeter cube, right? Which is pretty uh, which is kind of one of the light metals. Magnesium being 1.84, which is again a good candidate material, but corrosion being a main issue. So let's look into aluminum. That could be kind of one example I'm giving here. So if I take aluminum and look at the corrosion of aluminum, what the aluminum look like is a very reactive element. If you put aluminum in air, immediately it will form a thin oxide layer. We call it a passive film, and that's a kind of barrier that kind of separates the atmosphere from the metal and kind of prevents the metal from the corrosion, right? And looking at the Porbet diagram here in the right hand side, this aluminum oxide when you form is pretty stable. It's pretty stable at very high potentials. But the problem occurs if you have the salt present in the environment, like sodium chloride and things like that. What they would do is they would kind of break down the passive film. Once the passive film is broken down, you form a pit that could grow or could repassivate, right? So these materials are prone to corrosion, but due to this that passive layer, they kind of they perform okay. Like you can take pure aluminum, can use them in the kind of naval applications, and they would be fine. You can make the ships and out of them, they would be fine. But the main challenge comes is the aluminum. Pure aluminum is very soft, right? So what we do is, sorry for this busy slide here, but what I'm trying to show here is that we try to improve the properties, the mechanical properties of this material to make them useful. Being very soft, like 25 megapascal yield strength, kind of mm, uh, 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 25 megapascal yield strength of aluminum is kind of not allow them to be used in lots of engineering applications. So what been done is we develop like huge range of these aluminum alloys, and we divide it from 1 to 7,000 series alloys. And you see the properties varies from like 70 megapascal to here from 380 to 620 megapascal. And also 2000 series alloys used in some applications in aircrafts, right? So these are the high strength aluminum alloys. Now, the way we getting strength in these materials is basically by the precipitation hardening. We introduce additional phases. And if I look at this microstructure, how the microstructure varies if I increase the strength of the material. So you can think about this first image here. If you see my cursor here, that's a pure metal, right? So we don't have any particles present, and the corrosion resistance is like pretty similar to what pure aluminum has, right? And now as we adding alloying elements, what they do is they're forming some additional phases. You can think about these little particles present. So if I look at the far right hand figure, right, you see lots of these kind of blue particles present. We call them precipitates. They could be a few nanometer in length scale, and they are kind of closely spaced, and they provide all the strength. So they are needed. But from corrosion perspective, what is happening is their electrochemical properties are very different than the matrix, and they interact with the matrix, and what they do is they cause the localized corrosion, and the corrosion becomes a huge issue. So now I take pure aluminum, highly corrosion resistant. I go to 7075 T65 one we use in aircrafts. That has huge corrosion issues, right? So as we increasing the strength, we decrease the corrosion resistance. So if I plot corrosion resistance as a function of strength, and it's a very qualitative map, what we'll see is that as you're going from 1000 series to 7000 series alloys here, what is happening is you're increasing the strength, but your corrosion resistance decreasing a lot, right? Now, what would happen is if you can make really alloys which has high corrosion resistance, really high corrosion resistance, right? And also have very high yield strength. So the target being like a yield strength more than a gigapascal, and having corrosion resistance very similar to what stainless steels have. And so we put some of our hypotheses together and making kind of solid solution, and I'll go over it and see what we get, right? So now when it comes to improving the properties and kind of achieving these goals being kind of really here in the right top end of this graph here, we could have two strategies. We can take the commercial alloys and improve their corrosion resistance, right? And the second approach would be kind of making alloys, purely new alloys, and which have really good corrosion resistance. So the approach with the improving the corrosion resistance of commercial alloys kind of include is we do that, but the challenge is there. We could increase the corrosion resistance a little bit. We can solve very specific problems, but it becomes very difficult to going kind of the beyond those uh, limits of those commercial alloys, conventional property, crossing the conventional property limits is kind of difficult. But I'll give one example here, and kind of that shows how we can kind of work on the commercial alloys and kind of solve those very specific problems. So here is one example for 5083 aluminum alloys. This is aluminum magnesium alloys, and used quite a lot in making the shapes and things like that, right? And this particular alloy has 4.5% magnesium and little bit manganese. And the problem with the alloys is highly corrosion resistant. But once we put in the service life and the temperature exceeds say 50 degrees centigrade, what happens is that the supersaturated solid solution of aluminum magnesium decomposes, and anodic phase we call Mg2L3, that kind of uh, precipitates at the grain boundaries, and then grain boundaries corrodes, and you have huge intergranular corrosion issues, right? So what we did is we look into the problem, like what are the key factors which control the corrosion, and we kind of identified, okay, the size of the particles matter, the composition of the particles matter, and things like that. So we said, well, how can we solve those specific microstructural problems and enhance the corrosion resistance? And we said, well, we could have the microalloying, like add another element in very small amount, which can give us the desired properties, or we can have huge number of options over there. So that's why I started doing some the thermocales and thermodynamic calculations and kind of the modeling work. And we try to predict, okay, what could be those microalloying elements? What could be the heat treatments, which would give us the desired chemical composition of the matrix, desired chemical composition of the intermetallics and all that. And based on that, we predict, okay, what would be my the alloy, what would be the composition, what could be the heat treatments, and then we kind of make our material and test it. So here in the right hand side, one example, left hand side is kind of gives us the strategy, the roadmap, and the right hand side is gives like actual example. So what I'll do is I'll just show you the last one here. So the y-axis shows is the mass loss. That's kind of measure of the corrosion. So what we did is with this whole this approach of the thermodynamic calculations, we predicted that strontium could be one of the very useful elements in avoiding these all the corrosion issues. So here is example without any strontium. You see the weight loss like 25 milligram per centimeter square. As we add very small amount of strontium, 0.08 weight percent, and you see those values on the y-axis, that decreases quite a lot. So kind of that shows that how we could improve the corrosion resistance, and these thermodynamic calculations combined with our kind of those knowledge-based alloy design becomes a powerful tool in designing new material. But again, in these cases, what we're doing is we kind of making incremental change in the properties. Now, making like huge whole difference and kind of going like property limit, which we suggested like a gigapascal of yield strength and corrosion resistance similar to a stainless steel. We started looking at whole new compositional range, and I'll give an example anyway. But can we think about stainless aluminum and think about iron chromium alloy, which is kind of the base for most of the stainless steel. So in iron chromium alloys, what happens is iron doesn't have good corrosion resistance, but chromium is very corrosion resistant. At the same time, corrosion is very active metal, right? It as you put that in air, it's from a chromium oxide layer immediately. Now, if I make iron chromium alloys, what happens is iron dissolves, chromium stays as a chromium oxide in the surface, and eventually form the chromium oxide layer and gives all corrosion resistance. And so it should be a simple phenomena. We can do that for aluminum, right? We can make aluminum chromium alloys or similar to iron chromium alloys, we can make whole aluminum series. But the problem over here is like looking at the kind of phase diagram, say looking at aluminum moly or titanium, some of these phase diagram, the biggest problem is the solubility of these elements, right? So what we did was we took whole periodic table and kind of put the maximum solubility of different elements. So it's a kind of color coded map. So let's take one example like chromium here. The maximum solubility of chromium like 0.77 at weight percent. Vanadium is 0.4 weight percent, and these are the maximum solubilities. For example, vanadium's maximum solid solubility is 0.4 weight percent. If I go to the room temperature, this drops down to like 10 power minus 7 atomic percent. So what does that mean? If I make these alloys, these elements, they won't stay in the solid solution. They make some sort of precipitate. So what we did is just for the demonstration purpose, we make all these bunch of alloys like aluminum 5 atomic percent, chromium, titanium, and things like that. And what you see is that the matrix here, the grays thing, and you see that little brighter intermetallics, and they are kind of really big intermetallics. So if I make these alloys like that by the casting, what would happen is all these matrix would be corroded, so they're not going to be very useful. Now, if I want to make them, the hypothesis is if we make these materials in the solid solution somehow, we could actually probably get the good corrosion resistance similar to stainless steel, right? And also good mechanical properties. I'm not kind of talking about that, but I'll be happy to talk about those stuff later on. So what we did was to make the solid solution, we know there could be different techniques. One could be the ball milling, mechanical alloying, and we can put huge energy over there and can make the non-equilibrium supersaturated solid solution. So with that hope, what we did was we take these metal powders, we put them in a jar, and kind of we seal them in a glove box in high purity argon atmosphere. And later we learned that you really don't need high purity argon atmosphere, and having some air kind of could be even beneficial. But anyway, we just to have the control atmosphere, and kind of in order to understand the properties very well, we do all the processing in high purity environments. So anyway, we load our the jars, we put them in the ball mill, the simple system, and kind of perform the milling for some period of time. And if you are lucky, we get the powder like that. And if you're not, it might happen is that your all the jars are kind of coated with the powder and things like that. And then cleaning that powder is kind of a challenge. Once the powder is made, we can use the core compaction, sintering. We can use spark plasma sintering. So depending on what we want to do, we have different methods to kind of consolidate and make our samples. So if you look at here, our samples kind of more or less looks like that. We make small pellets and look at the properties. And also we can use this powder for additive manufacturing. We could use the powder for cold spray and variety of the application. Anyway, I'll quickly, I think given the time I have, I'll quickly kind of go through a few results here. So these are SEM images of all these different alloys we made. So this is just kind of example of 8 alloys. We have kind of a lot more alloys by now. And what really you see here is like if you look at aluminum and nickel, you kind of don't see a lot in the matrix, right? Looking at, say, aluminum titanium, for example, you start seeing a few bright particles here. In aluminum, chromium, and manganese, you see quite a few bright particles. Those are kind of intermetallics or undissolved solute, right? But if you look at this length scale is 2 micron here. So they're really small particles, right? And if I just to kind of compare them, if I make them by the casting from the different route, the microstructure looks something like here, right? And you see like 250 micron. So they're really coarse intermetallics. And if I don't have that, you see like really those alloying elements are uniformly distributed. And if I do like EDEX analysis here, like composition analysis in a volume, which could be like 5 micron kind of the diameter, you might see like all of these alloying elements are like if, are in the solid solution or in within that 5 micron volume, right? So what does that show is like these elements are very uniformly distributed in the matrix. We further did some TM and XRD analysis, which kind of confirms. So this is kind of just kind of show you how the material look like. This is the powder. The same images for the powder look like. And if you do SEM, how this particular alloy looks like, you have a few intermetallics present here and there. You have some impurity like iron-rich intermetallic. Otherwise, all the kind of the solute is kind of uniformly distributed. We do TM and we see like it's really small length scale now, and you can see that we start having kind of pretty complex microstructure. Initially, we thought it's going to be all uniform, but we see that vanadium, the solute rich and solute in regions. We also use the process controlling agent which introduce the carbon activities and carbon impurities and things like that. So this guy is kind of pretty interesting, the microstructure. At kind of micron scale, it looks pretty uniform. At nano scale, there are lots of heterogeneities there. But the alloy kind of contained the matrix with a grain size of around 29 nanometers. It has very high solid solubility of vanadium of the solute, right? So we further look into the grain size, kind of all comparing grain size of all these different material and kind of how much solute went in the solid solution. So the y-axis, the these blue bars are showing the grain size. So you see that the grain size remains always below 100 nanometers and kind of varies depending on what solute we use. The solid solubility of those solute again varies, but it can be like in case of moly, for example, you have around 3.7, 3.8% of the added elements, added solute was in the solid solution. So we added 5 atomic percent out of that 3.8% in the solid solution, which is huge because if we predict that from the phase diagram, these are kind of insoluble elements, right? So you have like 7, 8 orders of magnitude higher solid solubility. Anyway, now looking at the corrosion, the way we were looking that was looking at kind of pitting potential value. So if you look here in this graph, this chart show you the E value, the potential value, and they're showing two kind of the potential pitting and the transition potential. So higher these numbers, higher the corrosion resistance of the alloy would be, right? So if I take the pure aluminum here, this is pure aluminum on the far right corner, right? So in the beginning, if you remember, we talked that pure aluminum is most corrosion resistant among all this aluminum series of the alloy, right? So that's why we're taking that as a benchmark, the most corrosion resistant one. So if I compare the pitting potential of that with aluminum vanadium, for example, you see the huge increase in the pitting potential, huge increase in the transition potential. So what basically that indicates that these materials, the ball mill materials, they have really high corrosion resistance, right? Now, what we did was kind of just to see that in how that kind of those numbers varies if I do if I expose these materials in the real time, if we want to use them in, say, environmental exposure, we want to in the seawater and things like that. So what we did was we immersed these alloy in 0.01 molar sodium chloride for 6 months, and we were kind of monitoring the growth of those localized corrosion, the growth of the pits, right? And here for the comparison, we took the commercial alloys and pure aluminum, which are the commercial alloys which are really corrosion resistant. If I take 70, 75, those high strength ones, there the pit depth would be really, really huge. But even comparing those corrosion resistant alloys with the ball mill alloys, you see there is huge difference. In the ball mill materials, the pits form initially, but they don't grow. So if I analyze those pits, you see in like First few days, those pits has grown, and then they are kind of pretty much constant. There's not much pit growth. So what it shows is these materials are actually corrosion resistant and kind of verifies whatever electrochemical data we get. Now, putting this data like this corrosion resistance as a function of the strength. So you remember the graph I shown you in the beginning. We were plotting the corrosion resistance as a function of the strength, right? So here our commercial alloys are pure aluminum and high strength aluminum alloys. And what we did is the alloy we made here, actually we reached to this top right corner. So we have alloys which have kind of a gigapascal of yield strength and very high corrosion resistance. So that's all good. I mean, those materials could be made, and of course, further work could enhance the corrosion resistance. I mean, this is the work we did in 2018 actually. Right now, we have a lot more alloys which have really high, really better properties. But I think what becomes really interesting is we wanted to understand why that happens, right? And I guess understanding this fundamental mechanism would also help us in designing our strategies for future material development. So I would probably not go with all those mechanistic all the studies we did to develop mechanistic understanding. I'll show a few of them really cool ones. So one way I would show you some of the work we did with the TEM, the transmission electron microscopy, and try to understand the corrosion mechanisms, right? And also, it's pretty new use of the transmission electron microscopy in studying the corrosion is also pretty new thing. So I'll give you a few examples. So what we do is very simple experiments. We take our material, we put them in a corrosive environment or do certain corrosion test. Say, for example, sometime we want to study the passive film and we want to exclusively grow the passive film. I mean, grow the passive film means like the maximum thickness would be like 10 nanometers or something. So we have those passive film and we have those metals either after electrochemical tests or after simple immersion tests, right? We take them, we put them, take them to a 5E focus ion beam. We put deposit of platinum layer on top of them to kind of protect the material which gonna be kind of making a TM specimen out of that, and we kind of make the trench around it, both the side, and then we make like kind of this thin specimen there, and we kind of lift that and take that sample, very thin sample, to the TM, right? So what we're doing basically, think about this is my sample, and we're looking at the cross section of the sample, right? So now here how the passive film look like. So this is aluminum 5 vanadium alloy. This is kind of two examples. One is just taking the material and putting in air, right? We prepared the material and this had been stored in the glove box. And even that high purity environment, as we discussed that, right? I mean, taking pure aluminum, you to keep that in air and you immediately form a oxide film on that, right? So that's the oxide film we talk about. So we haven't done any electrochemical test on them, just in the air, and you see like 5.3 nanometer kind of surface film forms on that. And same thing here, after 2 hours immersion, there is a little growth in the surface film, like 7.1 nanometers, and kind of starts becoming a little uneven. So you have those surface film. So basically, we can see that surface film, and then we can study the different characteristics of the surface film. We can look at the crystal structure, the composition. We can look at the passive film and the metal interface. I mean, it's challenging. It's not easy job to do, but we have the opportunity to do all the stuff, right? So looking at how this composition looks like, so one thing we really realized was, if you look at these figures here, look at the one I'm showing here with the cursor. So it is 5.3 nanometer thick passive film, and the way we verify that's whether it's oxide or what that is, there is huge amount of oxygen present. So there should be either oxide or hydroxide, and things like that, right? And now looking at here, you see that aluminum enrichment, kind of this aluminum rich region outside, right? This is the matrix where there is huge aluminum rich region, and outside then you see kind of the aluminum lean and then aluminum rich, and then we see a vanadium rich region, and we superimpose. What we really learn is that the outer oxide is aluminum oxide, and the inner oxide or inner region is rich in vanadium, and all this vanadium is not oxidized. That's kind of metallic vanadium. So we learned that, well, vanadium kind of segregates just below a passive film, right? our initial hypothesis was something different. We initially thought that you would make exclusive vanadium oxide layer and that would prevent corrosion. So that wasn't the case, but you at least have the segregation of vanadium, and we kind of based on that we kind of further try to understand how much quality of the passive film would be, and we kind of understood quite a lot. Probably we don't have time today and uh, to go all the details. Another thing we learned was, and I'll talk a little bit about that too later on. We looked at the where the corrosion initiated. So this is one example. Again, this like you see, there's 500 nanometer, and so this region over here is a corrosion pit, right? So we start having had the background of the passive film, and we start forming those pits, right? And now, if I look at very closely inside the passive film, we have some regions where where some regions where I think some particles has fallen out, but we were able to isolate a particles which is iron rich, right? And we know that these iron rich particles they cause the corrosion in these aluminum vanadium alloys. This iron is coming as impurity. The milling media we were using was stainless steel, so some of those vanadium is coming from there, right? Now so we detected that, and what other thing we found was that there's lots of vanadium on that iron rich particle. So if I find iron rich particle inside the matrix, and if I do the EDX analysis, I won't find vanadium and aluminum together, but we find always vanadium on top of these aluminum rich particles once we're looking at the pits or somewhere regions close to the passive film. So that's kind of verifies one hypothesis we put in the beginning when we were designing the alloys was that the vanadium is kind of vanadium would be dissolving inside the pit, and it dissolves, it makes the vanadate, and vanadates are very well known corrosion inhibitors, right? So what those vanadates do is basically they kind of deposit on those iron rich particles, and as they deposit on the iron rich particles, they shut down their cathodic activity. So if you don't have enough cathodic activity, you cannot have this critical pit solution which is needed for the pit growth. So you can have lots of pits forming, but they don't grow because this vanadium could kind of redeposit on those cathodic particles and shut down the corrosion as it initiates. So that kind of helps in understanding what could be our future alloy design strategies. So we kind of have a number of kind of corrosion mechanisms, but probably I won't go through all of them. I'll just skip that. Another thing we learned was, and that was coming from different work on these aluminum based alloys. One thing we learned was we made some aluminum iron alloys, and probably I can talk about that later on. But our thought was that aluminum iron alloy may not give good corrosion resistance. We just wanted to see how bad corrosion resistance would be. But when we look into that, we got some surprising results, and pretty good, like in a surprising in the good sense. We had really good corrosion resistance. So one thing we learned from that work, and which would be applicable for a lot of alloy development stuff, would be conventionally what we think about is in aluminum alloys particularly, if I have a intermetallic present, for example here iron rich particle, right? What it does, it made the matrix corrode along it, and that iron rich particle, or that kind of it could be a constituent particle, it could be a inclusion, that serves as a local cathode, and everything else around that corrodes. Now you can think about if I have the same amount of inclusion, but you distribute that everywhere in the matrix, right? And kind of situation like over here on the right hand side, what could happen is that you can pit could form. Once your pit has formed, what you have is inside the pit you have lots of cathodes sitting, and those cathodes, due to their cathodic activity, they would produce lots of hydroxyl ions. Now, one necessary condition for pit growth is that the pH has to be really, really low. This could be like 5 molar HCl kind of situation inside the pit in that local environment. And what these small cathodes could do is they would never let that situation to come, and eventually pit would grow, pit would not grow, right? So anyway, I mean, I guess this kind of mechanism is pretty useful. I'll give one more quick example for same alloys. So now we talked about this making these aluminum and vanadium or wide range of aluminum alloys. Now it comes to what is the use of these materials. So of course the data I'm showing you, this is kind of, we took the powder, we kind of make small pellets out of them. But when it comes to making the real parts, so one aspect would be kind of making kind of some structural components. Another would be using them like coating or something. So this particular example shows some of those metallic coatings by the cold spray. where we can use our material like aluminum vanadium in this case as a feedstock, right? So we know that in the cold spray, what we do is we have a substrate and we kind of deposit our metal powder on the substrate. We kind of send the power particles with very high velocity, and the particles hit the substrate and kind of get cold welded on that, right? So in that way, we kind of develop a coating on the substrates, right? So here is one example for aluminum vanadium. I mean, what we did is just cold spray and just covered just the coated whole the surface with those vanadium. It was really thin layer. So you see example over here, very thin coating, like 5 to 20 micron thick coating, and it was nanocrystalline and things like that. We did all the microscopic characterization and so on. Now, what we really found was we did some potential dynamic polarization graphs. So the blue one shows you the cold sprayed material, and this red one is 2024 T3. So this is the substrate, right? So if I take the substrate without coating, I get graph like red one. If I take the substrate with the coating, I get graph like one with the blue, right? So anyway, uh, now I mean the difference is just the coating in these two cases. So what this shows is really huge improvement in corrosion resistance. So you look at the pitting potential values are very different. We did some EIS and things like that, and the huge improvement in the corrosion resistance. We look at the wear resistance improved quite a lot. uh, Okay, so one thing is really, really important here to notice is that if you look at their corrosion potentials, so our coated material is corrosion resistant at the same time, it is sacrificial. And why that is really important, right? I mean, we can take pure aluminum and you can think about coating pure aluminum with the chromium, with the nickel, with other corrosion resistant metals. But what happens is if you take the corrosion resistant metals, their corrosion potential is much higher than or more much higher than the substrate. And what does that mean is in case there is a coating breakdown, then what would happen is these corrosion resistant materials will not corrode, they would make the substrate to corrode, and that gonna be a huge problem if you want to use these materials in real life, right? You'll have like huge corrosion of the substrate. The situation could be worse than kind of the materials which was not uncoated, right? So these materials become like really unique. They are although corrosion resistant, like for example, think about coating with aluminum with chromium. At the same time, these materials, if there is a coating breakdown, they won't make the substrate corrode. They would corrode by themselves. And we measured kind of their corrosion rate in case there is a kind of coating breakdown. The corrosion rate of this coating would be very, 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 very small. And also they could release some vanadate and things like that. So that means they would be highly corrosion resistant coatings. We kind of did some long-term immersion tests. We didn't notice like huge corrosion issues after that and all that stuff. So I guess in summary, this kind of the making these aluminum alloys by these processes like ball milling and so on kind of could be very powerful techniques. So now I think we have the capability to make the material. We just have to think about how we're gonna use them and also develop like fundamental understanding and improve their properties, right? I mean, of course, there are lots of challenges. We cannot just, I mean, there are few properties we need a lot more than that. So that was one example. I think still we have some time, so I'll give just one more quick example, and let me know if I'm running out of time. But one quick example for additive manufacturing. So we all know that additive manufacturing being kind of used quite a lot these days, a lot of interest there. And just as kind of the video you can show there, here's a laser powder bed fusion method. What we do is you kind of you have a CAD model of the design you want to print, and you feed that to the computer, and based on that, there would be a laser which would be kind of hitting that powder bed, right? And print a layer of that component, and then you kind of lower down the platform, put new layer of the powder, and again repeat the process, and you will get the 3D printed parts, right? So I'll probably a lot of you would be kind of familiar with those additive manufacturing. So I'll just talk about it real quick, right? So now we looking at the very specifically additively manufactured stainless steel. So I mean, this is just kind of one example, a specific example, but the concepts, of course, you can use in many materials. So if I look at the say 316 stainless steel, and if you look at the corrosion, what are the factors which influence the corrosion? Of course, the material, right? The composition, the microstructure, what kind of defects are present there. So they are the main factors which influence the corrosion, right? Now, looking at those AM whole the AM process, there are lots of variables. You have kind of a feedstock where you start your material with, right? You have wide range of SPS, LPA, PBF, or the AM parameters. A lot of time we do those post processing treatment, and once we look at the post processing treatments, there could be different types. Processing parameters, again, there are different kind of huge amount of the processing parameters. So all these gonna influence your corrosion, right? And again, you have different kind of the defects present, right? You have different kind of microstructure coming up. So when we look into the literature and we look at the properties of these materials, and taking just one example for say corrosion property, we see like there is a huge body of the literature which shows that by AM you improve the corrosion resistance. And there is huge amount of literature present which says that if you do AM, your corrosion resistance would decrease. So there is huge discrepancy in the data present, right? So one thing we wanted to do is that kind of understand why there could be discrepancy in the data. Second thing is, can we really improve the corrosion resistance? Take this opportunity of having this new tool, right, and really improve the corrosion resistance. So what we started doing is we said, well, with this kind of motivation to avoid the post processing, improve the kind of the having the more reproducible properties and increase the corrosion resistance, right? So what basically we can do in that, right? So what we thought, I mean, our the starting powder is really important. That's 316 stainless steel powder, right? So we can use certain additive, right? And the thought was, if I say add additive that can carry, for example, nitrogen there, so I can make stainless steel which has very high nitrogen content, right? Otherwise you won't be able to make them, right? I mean, people did a lot of work like having high nitrogen containing stainless steels, but the challenge is the solubility of nitrogen is very limited. Now what is unique about the AM processes is the temperatures goes very high, right? And then the solidification rates could be very high. It could be like 10 to the power 7 Kelvin per second. So huge solidification rate. So you can dissolve that nitrogen in the material, and then you can retain it too, right? So okay, we kind of develop, we had thought for high nitrogen containing kind of more uniform microstructure, and then we learned that actually you don't necessarily need uniform microstructure and all that. So what simple thing we did was, we took those additives, milled them with the 316 stainless steel powder. So we buy them from the commercial vendors, mill them, and then we make our 3D printed coupons, and we look at their properties. If they are good, we try to understand why, what the mechanisms are. If you didn't get the result, we of course try to understand what happened there, and then we repeat the process, right? So there's lots of experimental work. So I'll just show you one example where what we do is, so when we make the powder, we mill the powder. Our aim is that during the milling process, we don't want to change the morphology of the powder at all, right? Because for the AM you need spherical particles, you need like certain size distribution and things like that. So we don't want this particle morphology to be affected at all, right? So we kind of optimize our milling parameters in a way that we're not doing that. So what we do is we take the additives, so in this case like cerium oxide, lanthanum nitride, chromium nitride, right? And we mill them for a certain period of time. And if you look at those individual powder in the EDX analysis, you see that you coated those particles with the chromium or nitrogen, and whatever additive we put in. So anyway, so we get that powder, and here I'm giving you just one quick example for chromium nitride. So we make this powder, make those chromium nitride modified powders, and use that for the 3D printing. And if I compare my as printed material without any chromium nitride with chromium nitride to XRD, kind of get the similar data. Look at kind of top surface. So this is the way the top surface SEM looks like, right? You print it and just take as receive surface. And they look pretty similar. They have kind of similar kind of oxide forming and all that stuff. Now we start looking at the microstructure, the cross-sectional microstructure, and side by side you have the one material printed with 316L, another 316L with chromium nitride. Looking at this kind of those melt pool and all that stuff, kind of pretty similar microstructure we see. The difference we start seeing that we go really careful SEM characterization, really high resolution once we go. What we start seeing is that there are some subcells present, like there you have the cellular structure like cells, and inside the cells you have subcells, and the subcells are kind of pretty refined if I put chromium nitride. Another thing we see the cell boundaries. Cell boundaries is pretty thick in case of 316L without chromium nitride. Chromium nitride kind of refined them. These are kind of the differences we've seen other than not really a lot. Now looking at the properties, and reason we were looking at those differences, because once we look into the properties there was like huge difference in the properties, right? So the one on the right hand side is chromium nitride. These are cyclic potentiodynamic polarization. This is rod, the one used the commercial alloys, just to buy from any commercial vendor, right? And here you have the one we make from 316L. So what we're looking basically is again the pitting potential. I understand that a lot of people will not be knowing those polarization graph, but I guess what we have is a really high pitting potential, really high repassivation potential. So if we compare from the commercial 316L, pretty similar chemical composition, but totally different corrosion performance. So these materials are very corrosion resistant to the pitting corrosion. So anyway, we did bunch of other tests. I guess looking at the time, I would not go in a lot of details here. I'll skip some slides. So we did lots of TM and stuff, and kind of tried to understand the corrosion mechanisms, which wasn't very easy. We learned quite a lot. I mean, initially we thought that it's very easy. We put lots of nitrogen that cause all the differences, but I think the mechanism is pretty different. Now we did some more work. Like we have bunch of other additives. We don't have to talk about them. We tried like 20 different additives. Another one was carbon nanotubes. We tried to coat these materials with the carbon nanotubes. Again, there was kind of whole different story, different motivation for doing that study. Initially, I thought that adding carbon nanotubes means your corrosion performance would be really poor. But what we learned was they also increase the corrosion performance and quite a lot, like pretty similar to carbon uh, chromium nitride. And that's where we kind of started learning a little more about what could be the other factors which should be contributing to the improve the corrosion resistance, and that's where we kind of learned that those small nano inclusions could be playing very important role. And we are probably not going in the whole discussion of these mechanisms. Each of them would be probably their own different topic, to probably talk for an hour or so. But uh, but I mean, what we learned from this work is that you can take the same chemical composition, but you can change the properties a lot by controlling the microstructure, right? And also, you're necessarily not don't need the homogeneous microstructure. These AM materials are really heterogeneous at a small length scales. So we have to really talk about, heterogeneous microstructures, probably not the worst one. How you distribute those heterogeneities in the microstructure, that is more important. And we can use all this stuff in kind of controlling the properties and kind of designing materials with the new properties with the same chemical composition. So I guess for the future, right now, I guess we are at the stage where we have advanced manufacturing techniques. We have new computational tools. We have really advanced characterization tools. So I guess using those, I guess we are in a position where we can explore whole new compositions. We really don't need to stick to the compositions we have, and we really need to kind of we could really for the kind of similar compositions you could probably design whole new microstructures, and we can go well beyond the conventional property limits. So I think all the and also all this a lot of understanding we're developing with these tools that kind of help us in predicting the life of the materials, kind of having the better way of managing the corrosion issues. And I guess for the future I think we could probably change whole kind of material landscape we have available. So with that, I think want to thank, I mean, all the work I presented, it came from all my students, of course, the old pictures, but all my PhD students, many of them graduated now and working different places, my collaborators, and of course funding from NSF, from DoD, from ONR, all that. I wanted to thank to all that. And with the time, I think I wanted to thank you all. And if you have any questions, and let me know. Thank you. And I'll probably stop
Any
sharing.
questions from participants? Okay, no questions.
Yeah, I mean, you can ask or you can also write. I'm seeing the chat section. So if you have any questions, feel free to write over there.
Yes, yes, sir. Okay, as we come to the close of this enlightening session, I would like to take a moment to express our sincerest gratitude to Rajiv Gupta for gracing us with her invaluable insights and expertise. On behalf of FDP and all the participants, I extend our heartfelt thanks to you. We look forward to the opportunity of welcoming you back in the future and continuing our engagement with your groundbreaking work. Thank you, sir. Dear participants, now we are moving towards our valedictory function. I hand over this session to Dr. Arvinder Kaur.
Thank you very much, ma'am. Ladies and gentlemen, it is said that to improve the golden moment of opportunity and catch the good that is in our reach is the great art of life. A very good evening to all of you. I, Dr. Arvinder Kaur, welcomes you all to valedictory function of International Faculty Development Program held on the topic 21st Century Recent Trends, Challenges and Future Roadmap for Transition in Technological Generation. We are feeling very privileged to have galaxy of intellectuals, honorable chief guest of today's program, head of our institute, special invitees, participants, professors, and students. Ladies and gentlemen, it is said that everything begins with an idea. Idea provoke imagination, and imagination thrives for improvement, and these together with proper implementation makes a program like this International Faculty Development Program. We are very fortunate to witness the budding engineers, faculty members, researchers, technocrats, and managers gathering a knowledge and molding them into concrete form so as to change the face of tomorrow. Ladies and gentlemen, it is said that a pessimist complains about the wind, an optimist tries to change it, and a leader adjusts the sail. The sails for this particular notion were adjusted by a person who gave us the belief to bring together this event. She is none other than Dr. Shubhangi Ratkantiwar. And now I invite ma'am to please tell us about this event. Over to you, ma'am.
Good afternoon, everyone. Honorable dignitaries on the virtual dais, Chief guest of today's valedictory program, Professor Raju Gupta, North Carolina State University, USA. Dr. Uday Waghe, Principal YCCE. Dr. Rajesh Thakre, Head of Department of Electronics Engineering and one of the convener of this program. Dr. Ujjwala Ghodeswar, co-convener of this program. Members of Organizing Committee of the International FDP and my dear participants. I am Professor Shubhangi Ratkantiwar, Professor in the Department of Electronics Engineering and convener of this Faculty Development Program. As we come to the close of this remarkable event, I am filled with an overwhelming sense of gratitude and accomplishment. On behalf of the organizing committee, I extend my heartfelt thanks to each and every one of you for your invaluable contribution to the success of this event. This 6-day faculty development program was envisioned as a platform to encourage meaningful interaction and networking among the faculty members around the world and distinguished intellectuals, academicians, and scientists from leading academic institutions and industries worldwide. First and foremost, I want to express my deepest appreciation to our 18 distinguished speakers who shared their insights on the future roadmap for transitions in technological generation across various disciplines. Day 1 of this faculty development program started with inaugural session and the keynote address of Dr. James Conrad, who is professor at University of North Carolina, USA. Next session was conducted by Dr. Vishwesh Kurane from Purdue University, USA, and the third session was delivered by Dr. Chetan Ralekar from MIT, USA, that is Massachusetts Institute of Technology. Second day of the International Faculty Development Program began with the presentation by Dr. Dolar from North Carolina State University, followed by the second session by Engineer Nitin Birla from Kuwait Gulf Oil Company, and the third session of day 2 was conducted by Abigail Sykes from North Carolina State University. Day 3, that is April 27, 2024, began with a nice session delivered by Jitendra Vaidya and ended with the session delivered by Professor Ramesh Agarwal from Washington University, USA. The sessions planned on day 4 were by the speakers Mayuresh Dow, Intel USA, Sumit Pandey, Microsoft USA, and the participants had a great takeaways from the session conducted by Dr. Deepak Vaikar, Singapore. On day 5, the sessions were delivered by David Haney, Director, Codebase, Texas, USA; Dr. Amruta Chimote, University of Technology and Applied Science, Al Musana, Oman; and Dr. Lavanya Rachakunda from North University of North Carolina, Wilmington, USA. On day 6, that is the last day of International Faculty Development Program, the sessions were delivered by Dr. Hemant Pendharkar, University of South Florida, USA; Dr. Shashwat Ratkantiwar, Director, Research, Lead Thinking Research Center, Florida, USA; and Dr. Rajiv Gupta, who is the chief guest for today's valedictory session from North Carolina State University, USA. All these speakers threw light on the basic facts of developing world-class organization and India thereafter. They also suggested to enhance the academic collaboration with best ranked institution, to lead with an insightful roadmap and action plans, include SWOT analysis and competitive analysis, diversify faculty to foster innovations, focus on research, improve engagement levels, increase motivation among the faculty members. Their representation were both enlightening and inspiring, sparking engaging discussion and fostering new ideas within the diverse audience. We deeply appreciate the time and effort the speakers have dedicated in preparing and delivering their presentations. Their commitment to excellence and professionalism shown through every aspect of their involvement, leaving a lasting impression on all who had the privilege of hearing. Their expertise, insights, and passion illuminated our discussions, inspired new ideas, and elevated the quality of discourse throughout the faculty development program. Moreover, their willingness to share their knowledge and experiences enhance the geographical boundaries, further highlighting the global impact of our international faculty development program. Their presence elevated the quality of discourse and reinforced our commitment to fostering the international collaboration and understanding. The basic objective for this faculty development program, for in view of the faculty members participating in this FDP, was to enhance their interdisciplinary knowledge, foster innovative ideas, pursue high quality research, and engage the academic partnership both nationally and internationally. And essentially, this program is sought to equip the participants from various engineering and science fields with expansive insights and a strategy to advance their research and development pursuits. As today marks the conclusion of this FDP, it is my hope that the past 6 days have provided all the faculty members with memorable learning, research, and networking experiences. I am assured that the participants have gained valuable insights from each session. About 742 participants from different states of India and from different countries might have gained a huge takeaways from every session. So highlights in terms of this particular IDFP 2024. First highlight is global representation in terms of speakers and attendees. So we have the speakers from top ranked universities and industries from various countries including USA, Singapore, Kuwait and Bangladesh and Oman. Total number of Zoom participants were 742, but additional participants were joining through the YouTube live streaming. So this particular number of participants may exceed 1000. Then we have got the participation from USA, Canada, Kuwait, Germany and India. And we were getting excellent feedback for each session from the attendees. It is fair to conclude that this FDP was a resounding success. Such an event does not come together overnight. The wheels started rolling months ago and years ago. It demanded extensive planning and meticulous execution. Numerous individuals have contributed in various ways to transform this event into a seamlessly organized meetings with numerous intriguing presentations and excellent environment for discussion and networking. I have been fortunate to have support of the team of highly motivated and dedicated colleagues at YCCE. Dear organizing team members, your tireless efforts behind the scenes have been instrumental in ensuring the smooth execution of every aspect of this conference. From logistics to programming, your attention to detail and commitment to excellence have not gone unnoticed. I cannot express enough gratitude to everyone for their involvement and their readiness to undertake the tasks well outside their comfort zones. I would like to take this opportunity to express my sincere gratitude to Honorable Dattaji Mekhe, Raviji Mekhe, Samirji Mekhe, Vrindaji Mekhe, and Raghavji Mekhe. In closing the session, I am filled with optimism and excitement for the future of engineering technologies and science, and I am hopeful that the connections formed and ideas exchanged during this FDP shall serve as a foundation upon which we can build a brighter, more collaborative future. Thank you once again for your participation, your passion, and your commitment to excellence. Together, we can continue to push the boundaries of knowledge and innovations. Thank you all. Thank you speakers and thank you participants. Thank you organizing team members. Thank you.
Thank you very much, ma'am, for such a nice briefing about the IFTP. Ladies and gentlemen, it is said that nothing great will be achieved without great men, and men are only great if they are determined to do so. And this truly applies to a person who is chief guest of today's program, that is Dr. Rajiv Gupta from North Carolina State University. Now, I invite Sir to please share his wise words on this IFTP. Over to you, sir. I think due to some technical problem, he is not there in this. So let it be. Ladies and gentlemen, it is said that personality is not set in stone. It's a constantly evolving force shaped by your experience and choices. And today on this occasion, we have with us HOD of Electronics Engineering Department, Dr. R.D. Thakre. Now I request sir to please share your views on IFTP. Over to you, sir. Thakre sir, over to you.
Hello, whether I'm audible?
Yes, sir, you are audible, sir.
Good afternoon, everyone, all the participants who have joined this international FDP. First of all, myself, Dr. R.D. Thakre, Head of the Electronics Engineering Department, welcome this closing ceremony of this international workshop for last 6 days. As you know that Yashwantrao Chauhan College of Engineering. Yes or no? Whether
Rajiv Gupta.
Hello. Yashwantrao Chauhan College of Engineering was established in 1984. The college is NAC accredited with a grade of A++, having highest score in the Maharashtra. Our department, that is Department of Electronics Engineering, also is the pioneer department of Yashwantrao Chauhan College of Engineering, which was started in 1984 with an intake of 60. Now the present intake is 120. The department has completed the 5 cycles of NBA accreditation, and I am happy to share that our department got the 6 years of NBA accreditation. The faculties are well qualified with the PhD qualifications, and they are publishing the papers in SCI and Scopus journals. Again, the total number of patent granted till date is 14. This is the big achievement of the department is concerned. This is our second international FDP, that is the 21st century, the recent trends, challenges, and future roadmap for transition in technology generation from which was conducted from 25th to the today's date is 30 April 2024. As you know that the technology is changing from day to day. The purpose is the societal life becomes smooth. There are tremendous opportunity, as you know that in artificial intelligence, deep learning, machine learning. As you know that in the today's scenario, the education, we are using the various tools such as a chat GPT. There are 3 things required, that is the transformation, attitude, and learning for the new things. But without faculty, it is not possible to use any tool for learning so that the learning must be enthusiastic and is possible for the last student who can learn the things very easily. The purpose of this international FDP is to motivate the faculty to interact with all the intellectuals from the world. All the participants and the faculty members are having the opportunity to interact with these persons for any collaborative work such as a paper presentation or conducting conference or the proposals, because nowadays this research atmosphere is very, very important, because for every college has to grow, these things are very important. The main challenges for the future related to healthcare sector, then agriculture and industrial sector. One of the expert has already mentioned that when we are talking about industry 4.0, 5.0, similarly there is agriculture 1.0, agriculture 2.0 and agriculture 3.0. Because you know that the India is an agriculture country, so there is a tremendous scope for having a research in this agriculture sector. Then as you know that again the new fields are Internet of Things, and so for that case the learning with AI is very, very important. As rightly said by Dr. Ratkantiwar Madam, who is the convener of this program, we have covered so many things from these all the experts, and which will be very, very useful for your learning is concerned. Because see that this is the second time we are conducting this international FDP. This FDP was successful because of the first thing, because of your experts. Then what are the participants you are joining from India as well as the abroad? See that we got various tremendous response. That is the 742 participants, and joining these participants for every lecture is very important. I know that when there is a very good feedback from the participants also, because the speakers are very good, and this is the important thing for the success of this international FDP is concerned. Remember that when anything we have to conduct, our faculty members have taken a lot of efforts. Without their efforts, it is not possible to conduct this IFDP. Again, the important thing that is we have a consistent efforts from our management, our principal, our deans, our HODs. Because of this is the successful international FDP. We are always ready to the participants that if they are having any problem related to what are the things they are getting from this FDP, we are ready to share with them. So thank you very much. I'm very much thankful to all the participants for this international FDP is concerned. Thank you. Thank you, sir.
Thank you very much, sir. Ladies and gentlemen, Dr. Rajiv Gupta, who is from North Carolina State University and who is the chief guest of today's program, has joined us back. And I'd like to invite sir to please share your views on this IFTP. Over to you, sir. I think there's some technical issue. So till it gets resolved, I would appreciate if somebody will share their views on this IFTP. So I invite any attendees or any participants They may come forward and share their views.
Hello. Hello. Am I audible? Hello.
Yes, ma'am.
Yes, ma'am.
Yeah. Good afternoon, everyone. Yeah, I'm Dr. Purva Vaingankar from Mumbai. First of all, I would like to congratulate the entire team of Yashwantrao Chavan College of Engineering. Such a excellent effort in organizing this. So hats off to them. And all the sessions were very well organized and very well planned. And there was zero technical error, because which is very important when in conducting such program. And all the sessions started on time and ended on time.
Vangi,
And the speakers
Vangi,
also were from very
Vangi,
eminent.
4:30 वाजले ना. 4:15 म्हणे तू उठवलं ना तुला.
Can you mute? Somebody's talking in between. Yeah. So I congratulate once again entire team. And yeah, we could learn right from AI, Chat GPT, to even novel devices from semiconductors. And the last session was something which was very different for my domain, but still it was really interesting. So various aspects of technology were touched upon, and very nicely conducted program. So I again congratulate entire team. And one small suggestion. So if it is possible to get either links of these videos, whatever you have recorded, that if we get, so that if we want to refer any content, so later on we can refer to that speaker. So if we get this list of videos, then that will be really appreciated, or their gist of their talks, whatever is possible. So it is my request to organizing team. Thank you so much.
Yes, thank you very much, ma'am, for your wise words. And definitely, we are going to provide all the links and relevant materials to you shortly.
Thank you.
And we will appreciate if anybody come forward and share their views. Still, this forum is open. I think Ms. Satyavati is there. Please unmute yourself.
Yes, I am here.
Yes.
Hmm.
Yes, you are audible. Yeah, please go.
Yes, I am audible. Good afternoon, everyone. Really, it's very good, very good, and I enjoyed really very well. My name is Sachivati. I am ex-colleague of Shubhangi Ratkantiwar when we started our career, and I am also mother of Rajkonda Lavanya. Okay. My huge congratulations to all the team. Mainly teamwork is here important. My huge congratulations to my friend Dr. Shubhangi Ratkantiwar and her team on the phenomenal success of this event. 6-day event. 6-day event, that too in time everything happened. It's very good. It's her hard work and dedication have truly paid off. So proud of you and your team. The impact of your hard work will be felt for a long time, and the memories created will be cherished by all the participants who attended. You should be incredibly proud of yourself and your team. I am really very happy that I attended all these sessions, and I also gave my feedback also. May this achievement be just the beginning, and I hope many more to come. Okay, thank you for everything. And in every lecture, I learned something new. In every lecture, something new is there. It's very nice. All speakers are good, and everything is happened very well. Thank you very much.
Thank you very much, ma'am. It's really very overwhelming, and we are really moved. Now we can take up We can take up one more feedback, and if anybody wants to share their views, they can come forward. I request all to please unmute, please mute yourself.
हो ते काय खाणं नाही होत.
Okay. As we have come to the closure of our valedictory ceremony, I invite Dr. Ujjwala Dhuleshwar ma'am to please propose the formal vote of thanks.
Ma'am, you unmute all. You mute all.
Good afternoon, all. Thank you is such a prayer that cannot be seen or touched. It must be felt by heart. I feel honored and privileged to get an opportunity to propose a vote of thanks on this special occasion. I am Dr. Ujjwala Dhuleshwar. On behalf of organizing committee of this faculty development program, I would like to acknowledge the personalities who have provided support in some form and who were with us during this long journey of almost 6 to 7 months in planning and executing the entire event. I would like to thank our honorable management, especially our chief advisor, Honorable Brenda Beckerman, for giving us opportunity to organize this faculty development program at global level. I am also thankful to Dr. UP Vati sir, principal, for helping us in obtaining the necessary administrative approval for organizing the event in campus in online mode. Words are not enough to thank Dr. Manali Sagar ma'am. Our dreams come true because of her constant guidance and support. Thanks, ma'am, for supporting our idea, for creating an opportunity to interact with intellects across the world. I would thank Dr. Salif Chauhan, Chairman, IIT Nagpur Section, and Dr. Suresh Rangankar, Honorable Secretary, IIT Nagpur Section, for their support and commitment to advancing the goals of this IoT. I also thank him for approving this activity through IIT. I convey my deep regards and hearty thanks to all the invited speakers for accepting our invitation. All the speakers are from eminent universities and industries. I would mention their names here. Dr. James Conrad, University of North Carolina, Charlotte, USA. Vishwesh Purani, Purdue University, USA. Dr. Chetan Raikar, Massachusetts Institute of Technology, USA. Dr. Dola, North Carolina State University, USA. Nitin Villa, Specialist Engineering and Projects Kuwait Gulf Oil Company, Attacker Cyprus, North Carolina State University, USA. Jitendra Vaikya, Founding CEO and Board Member, Planet Square. Shamit Mohammed, Jahangir Nagar University, Dhaka, Bangladesh. Ramesh Agrawal, Washington University, St. Louis, USA. Mayuresh Daud, SSC RTL Design Engineer, Intel Corporation. Dr. Deepak Vaikar, Chair, IEEE Education Society, Singapore Chapter. Sumit Pandey, Senior Software Engineer, Microsoft. David Hanif, Director, Codebase, Texas, USA. Dr. Amruta Chimoti, Al Musana, Oman. Dr. Lavanya Rajkumar, University of North Carolina, Wilmington, USA. Dr. Rajiv Gupta, North Carolina State University, USA. Dr. Shashwat Rattantiwar, Director, Lead Thinking Semiconductor Research Center, USA. Hemant Pendharkar, University of South Florida, USA. I would like to thank Professor Manish Hadak for providing us technical support. I would like to thank our HOD, Dr. Rajesh Thakre sir, for his help and support at various stages. An event of this dimension cannot happen overnight. The wheels start rolling months in advance. We have been fortunate enough to be getting constant guidance from Dr. Shubhangi Rattandiwar, convener of this program, that radiated a source of energy within us. Her ideas always moved around developing academic collaborations at global level. We will ever remain grateful to you, ma'am. I am very much thankful to all our faculty colleagues and non-teaching staff members who always stand by us and motivate us. I would especially thank Dr. T.G. Pansi for coordinating all activities required to conduct everything smoothly. Professor Atish Veshikivase and entire technical committee to take efforts to meet the real-time challenges of this program to be conducted in fully online mode. How can I forget to appreciate efforts made by Dr. P.G. Pansi, Professor Swati Nitmale, and Dr. Shweta Dhumst in developing and presenting the institute. I also acknowledge huge efforts taken by Vinesh Patil, a student from CSC Bank, for preparing the brochure and banner, which was highly appreciated by all the speakers and participants, and a team of students Amok Nagarkar, Bharati, Jagruti, Aditi, Himanshu Gajvi, Durgesh, Priyanshu for providing help throughout. I would like to take this opportunity to thank Dr. Arvinder Korma for her excellent anchoring during inaugural and valedictory sessions. I feel proud and thank all our organizing committee members and dedicated student volunteers. I cannot thank everyone enough for the involvement they have shown and the willingness they have expressed to take on the completion of tasks beyond their comfort zones. Last but not the least, I would thank all the participants for getting connected with us. If time is money, then today you have spent millions for us. Thanks to all of you for making this event successful. Thank you. Thank you all. I declare that the session, valedictory session is completed. Please fill the feedback form. Participant can fill the feedback form and then leave the session.